In this section, we're going to be looking at another ranking system. This time we'll be looking at the Spearman rank correlation coefficient. And let me write down some things here. Recall that the correlation coefficient R measures the strength of the linear relationship between the X and Y variables. To rely on R, we need 1, X and Y are linearly related. The variables X and Y have a bivariate normal distribution. For the Spearman rank correlation coefficient, makes no such assumptions. We will use paired data X sub I, Y sub I, and we will rank the Xi's and Yi's if there are no or very few repeats in the rankings, then we use the test statistic. It'll go by R sub S, and that equals 1 minus 6 times the sum of a bunch of d squares divided by n times n squared minus 1. N, that equals the number of pairs Xi, Yi. T is the difference in the rank of X sub I and Y sub I. I call it D sub I because each entry in there is going to correspond to one I for X and Y combined. Now, a couple of things that you need to know are, for one, we could have that R sub S goes anywhere between -1 and 1, including -1 and 1. In fact, if r sub s equals 1, look up here. If r sub s is equal to 1, that means this whole chunk has to be 0, which means that this sum of d squares is equal to 0, but each of these is a non-negative number, each of these, because you've squared it. And so if you add up a bunch of non-negative numbers and you end up with 0, that means each and every item in that sum had to be 0. So this means that every single difference in the rankings is 0. So if you have r sub s equals 1, this tells us that I should say it this way. The rank of x sub I equals the rank of y sub I for every possible I. What that means is there's no differences. The ranks are identical for xi and yi. Now, if r sub s equals -1, this tells you that the ranks of x appear in reverse to those of y. And then finally, this last one, r sub s equals 0, there is no linear relationship whatsoever. Everything else between those numbers are various degrees of a linear relationship. R sub s is used to estimate the population correlation coefficient rho sub s. Our hypotheses take the form, you'll have h sub 0, we'll say rho sub s equals 0. That means there's no linear relationship between the x and y variables for the population of x and y's. And h sub a means that rho sub s does not equal 0. That means there is going to be some sort of a linear relationship between the variables x and y. We use the Spearman rank correlation coefficient table to determine critical values. For these tests, testing the significance of the Spearman rank correlation coefficient as usual, most of the stuff is you're going to be doing the exact steps as we did for every other problem with a few differences here and there. So first off is list h sub naught and h sub a. Specify alpha. Use the Spearman table to determine the critical value. Our test stat, that is R sub S equals 1 minus 6 times the sum of d squares divided by n times n squared minus 1. Make the decision. All right, here's our first example. I can make life easier on you in the following format. H sub 0 and H sub A. For this section, they're always the same. Rho sub S does equal 0, or rho sub S does not equal 0. Rho sub S equals 0 means that there's no linear relationship. Rho sub S does not equal to 0 means that there is some linear relationship. So let's take a look at the problem here, and it says, can you conclude that there is a significant correlation between the overall score and the price? Is there a correlation? That means this second one is the claim. That means that there is some sort of a correlation. Now let's go ahead and write down what we have here. This is the way we want to work it. Let's get our list of x's and simply write them down. 77, 75, 73, 71, 66, 66, 64, 62, and 58. Now, before I do the y's, I want to rank these. Let me count the total number of data that we have so far. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 pieces of data. So we want to rank from 1 through 9. So we want to rank 1, 2, 3, 4, 5, 6, 7, 8, 9. Now they've made it sort of simple on us because the smallest number is at the bottom and it just kind of works its way up. So I will go up from there. Now I have one repeat here, and that is the 66s. These normally want to take up data items 4 and 5, but since they're the same, I take 4 plus 5. The average of 4 and 5 is 4.5. There, I've used 4 and 5 up now, and now I'll move on. 6, 7, 8, and 9. So I've got those ranks. Now let me get my y's. 3,700, 1,700, 1,300, 900, 1,000, 1,400, 1,800, 1,700. And as the x's, I'm going to do the same with my y's. So let me get the ranks for my y's also. Well, it's easy to see the smallest ones because they have fewer digits than the rest. So I put a 1 next to 700 and a 1 next, or a 2 next to the 900. Now I think I see some repeats for the y's as well. Let me come back and check that. I see more than 1,000 for the y. I do see more than 1,000 for them. So because it's possible for me to lose track, let me get all my possible rank numbers down. I've already taken care of 1, 2, and now I'll move on to 3. And indeed, the third one looks like it is 1,000, but unfortunately there's another one that's 1,000, so they're going to occupy spots 3 and 4. So the average of 3 and 4 is 3.5. Get rid of those. All right, now let me pick up with 5. It looks like 1400 is my next. And then 6 looks like, I was wrong about my 1400. That was 1300. And now it takes care of 1400. 7 looks like the 1700. 8 looks like the 1800. And then 9 looks like the 3700. And then now let's go ahead and get our values for D. This is where you take the difference of the ranks. So for this first row here, I have a rank of 9 minus a rank of 9. That gives me a 0. Next, 8 minus 7 is 1. 7 minus 5 is 2. 6 minus 2 is 4. 4.5 minus 3.5 is 1. 4.5 minus 6 is negative 1.5. 3 minus 8 is negative 5. 2 minus 3.5 is negative 1.5. And then finally, 1 minus 1 is 0. Now, before I add up all these D's, I want to square them. This is very easy to do. Notice that all of these numbers now become non-negative. And now I'm ready to add them all up. Probably shouldn't be too bad. Let me see, I got 1 plus 4 is 5, 21, 22, 47 plus 4.5 is 51.5. Now let's go ahead and get our test statistic. We have R sub S equals 1 minus 6 times the sum of D squareds all over n times n squared minus 1. Now this is our sum of D squared, so I got 51.5. And the total number of pairs was 9. So we have 9 times 9 squared is 81 minus 1 will make that an 80. And then let me get my calculator out to compute this number. 1 minus 6 times 51.5. And then I'm going to divide. Now put this denominator in parentheses or you won't divide by the whole thing. So put 9 times 80 inside of parentheses. So it attaches it to the fraction. And I get about 0.571. So R sub S is approximately 0.571. Now the critical value. All I really need to know for the critical value is my alpha. And the alpha here is 0.05. And I don't have a notation for this other than to call it CV for critical value. What I want is the Spearman coefficient table. So let me go and find it on my desktop. Here it is. Here we go. So my n is 9, so there it is. And then I need to find alpha equals 0.05, and I see I have it. For the 9 row and the alpha equals 0.05 column, I have 0.700 is my critical value. This is really simple. This kind of test only has one type of way it works. Now, since R sub S is less than CV, we do not reject H sub 0. If it were greater than CV, then you would reject. That's all there is to it. You don't have to memorize anything other than that. All right, in this example here, we have some achievement scores for science and math, along with the gross national incomes of 9 randomly selected countries for a recent year. So here they are. What I want to do is I'm just going to be looking, is there some sort of a correlation between the mathematics average and the gross national income? Is there some connection between the two of them? So I am going to let my mathematics average, I'm going to let X be that and my Y be the GNI. So in my X list, let me go ahead and put my rankings. Now I happen to know that there's 9 of them. So I'm going to start putting my rankings next to them. So I know 408 is the smallest, so I'll put a 1 next to that. 470 looks like the next one. What is after that? 486 is number 3. After that, 490 is number 4. After that one, we have 493 is number 5. And then we have 494 is 6. 506 is number 7. 516 is 8. And then 532 will be 9. Now let me do the same for the GNIs. It's easy to spot number 1. That's very fast. And in fact, I can spot the last one too. The United States has the largest GNI. And now I have to just start putting in my numbers 2 through 8. So it looks like 1143 gets a 2. Let me see, the 1192 looks like the next one. After that, the 1529 looks like the next one. The 1815 is number 5. And then I'm going to be moving on to the 2000, so number 6 there. And then I have already got 9 taken care of, and then I just need to do 7 and 8. Here's 7, and then there's 8. And now let me get their differences. So I'll start with this first one. 8 minus 4 gives me 4. 5 minus 6 gives me negative 1. 7 minus 7, there's a 0. 4 minus 5 is negative 1. 9 minus 8 is 1. 1 minus 2 is negative 1. 3 minus 3 is 0. 6 minus 1 is 5. 2 minus 9 is negative 7. And now let me get my d squareds. And let me add them all up. Let's see, 49 plus 25 is 74. 75, 76, 77, 78, 94. For a test stat then, R sub S equals 1 minus 6 times the sum of the d squareds all over n times n squared minus 1. That equals 1 minus 6 times 94 divided by 9 times 9 squared minus 1. That equals 1 minus, I'm not going to do any multiplication on my own. I'll let my calculator do all that. But I'll have 9 times 80 just as in the previous problem. So I get about 0.217. That, of course, was the test statistic. For the critical value, we have alpha equals 0.10, n equals 9. Let's go ahead and pull up that table. 9, that's 0.60 out of the table. So CV equals 0.600. Now, since my test stat, since R sub S is less than CV, we do not reject H sub 0.